Hello all. Let us now discuss about TE, TM and TEM modes in electromagnetic waves. So here we will be discussing about the three modes, TE mode, TM mode and then TEM mode. So when electromagnetic waves propagate through a guiding structure such as a waveguide or a transmission line, the fields are constrained by the geometry and the electrical properties of the conducting boundaries. So these constraints arise from Maxwell's equations and the boundary conditions and the conducting surfaces, which required the tangential component of the electric field to be zero at the walls. Because of these restrictions, the fields cannot assume arbitrary distributions. Instead, they form specific patterns known as modes. So each mode represents a unique way in which electric and magnetic fields vary in space while propagating along the guide. So, waveguide, it is a hollow metallic structure for guiding electromagnetic waves. So, these waveguides operates mainly at the microwave frequencies. So, there are two types of waveguides. First one is rectangular waveguide and then circular waveguide. So these waveguides are used in radar, satellite and microwave systems. So why does the modes exist in waveguides? The tangential electric field must be zero at the conducting walls always, and then the fields form standing waves in the transverse direction and the traveling waves along the guide axis, and the boundary conditions determine the possible modes. So based on longitudinal field components, the modes are classified into transverse electric mode, transverse magnetic mode, transverse electromagnetic mode, and then here the assumption is that it is propagating along the Z direction. The first one is transverse electric mode. So in transverse electric mode or TE mode, the defining characteristic is that the electric field has no component along the direction of the propagation. If the wave is assumed to propagate along z-axis, then the longitudinal electric field component is zero, while the magnetic field does have a longitudinal component. This means that the electric field exists entirely in plane transverse to the direction of propagation, whereas the magnetic field has both transverse and longitudinal components. The absence of the longitudinal electric field arises directly from the boundary conditions imposed by the conducting walls of the waveguide. So in TE modes, the electric field lines forms closed patterns within the each cross section of the waveguide and are always perpendicular to the direction of propagation. So these field patterns are determined by solving Maxwell's equation subjected to the boundary condition, resulting in standing wave variation in the transverse direction, and a traveling wave along the guide exists. So each T mode is actually identified by two integers, that is m and then n, which represents the number of half wavelength variation of the field in the transverse dimensions of the waveguide. For example, the T10 mode is the rectangular waveguide has a half wave variation across the wider dimension and no variation across the narrower dimension. An important property of TE modes is that existence of a cutoff frequency. So below this frequency, the mode cannot propagate and the electromagnetic fields cannot decay exponentially along the length of the waveguide. Physically, this occurs because the wave cannot satisfy both boundary condition and the phase propagation requirements at lower frequencies. Above the cutoff frequency, the wave propagates with a phase velocity greater than the speed of light in free space. Although the group velocity, which represents the energy transport, is always less than the speed of the light, among all TE modes in the rectangular waveguide, TE10 mode has the lowest cutoff frequency and is therefore called the dominant mode. So due to its low attenuation and simple field structure, it is widely used in practical microwave systems such as rectangular waveguides, microwave ovens, radar systems, satellite communication, and then microwave transmitters. And the next one is transverse magnetic or TM mode. In the transverse magnetic mode, the magnetic field has no component along the direction of propagation, while the electric field possesses a longitudinal component. This means that the longitudinal magnetic field component is zero, and the electric field has both transverse and longitudinal components. The presence of the longitudinal electric field distinguishes TM modes clearly from TE modes and results in a different field configuration inside the waveguide. In TM modes, the electric fields originate and terminate on the conducting walls of the waveguide, since the electric field lines must always begin and end on the charges. The longitudinal electric field component plays a significant role in shaping the overall field distribution. Like TM modes also characterized by two integers m and then n, which describe the number of half wavelength variation of the fields in the transverse directions. However, the TM00 mode does not exist because such a configuration cannot satisfy the boundary condition of the waveguide. So TM modes always exhibit cutoff frequencies, and these cutoff frequencies are generally higher than that of the TE modes cutoff frequencies for the same waveguide dimension. So this makes TM modes less commonly used in practical compared to the dominant TE mode. As the TE modes, the phase velocity of TM modes exceed the speed of light above cutoff, while the group velocity remains below it. The TM modes are mainly studied for theoretical completeness and are sometimes used in specialized applications involving field interactions with materials inside the waveguides. The next is transverse electromagnetic mode or TEM mode. The TEM mode or transverse electromagnetic mode represents a fundamentally different type of wave propagation. So in TEM mode, the electric field and magnetic field are entirely transverse to the direction of propagation, meaning that neither field has a longitudinal component. This type of wave closely resembles a plain electromagnetic wave propagating in free space because there are no longitudinal field components. That fields satisfy Maxwell's equation in much simpler form compared to TE and TM modes. The key feature of TEM modes is that absence of cutoff frequency, and it can propagate at all frequencies. Phase velocity equals to the speed of light in the medium, and it requires only two conductors. So TEM mode exists in coaxial cables, parallel plate transmission lines, twisted pair cables, and does not exist in hollow waveguides. The phase velocity of TEM waves is equal to the speed of light in the medium, and power transmission is highly efficient with a minimal dispersion. So the reason for TEM mode cannot exist in hollow waveguide lies in the boundary condition and the structure of Maxwell's equation. So in a single conductor system, it is impossible to satisfy the condition that both a longitudinal electric and magnetic field components are zero while maintaining non-zero transverse fields. Consequently, waveguides inherently support only TE and TM modes. So this fundamental distinction explains why waveguides are used primarily at microwave frequencies where TE and TM modes can propagate efficiently above their cutoff frequencies. So, as a summary, so TE mode, it has no longitudinal electric field. TM mode, it does not have longitudinal magnetic field. TEM mode, no longitudinal fields. TE and TM exist in waveguides. TEM exists only in the transmission lines. So thus conclusion is that TE, TM and TEM modes are essential for microwave study, microwave engineering and antenna systems, radar and satellite communication. So the dominant mode operation ensures efficient transformation. So a thorough understanding of these modes is essential for analyzing the wave propagation in different applications. Thank you.